All right. So let us quickly wrap up our portion before what is there for Cat 2. So as we remember, we have started with module number 6, and only a portion of module 6 is there in your syllabus. And in last day's class, we had started with a very interesting topic, as in terms of the MIMO systems. And if you remember, the basic objective behind this portion was to model a MIMO system in the form of y equal to hx plus n, which we already know as a CISO system. But now, instead of single input and single output, if I happens to have R cross T matrix, that is R receive antenna and T transmitted antenna, in that case, how we are going to define the particular matrix is one of the factor here, because the main objective here is that this channel matrix that we are looking at, this will play eventually a very important role in leading forward to designing many systems. All right. So even if you observe that even for MRC or EGC, when we had done that for diversity, there also we came across that H played an important role in finding out what is the optimal weight, or even the SNR calculations everywhere. So keeping that in mind, we found out that this MIMO channel matrix, which usually is referred to as R cross T matrix, is nothing but a combination of receiver and transmitter antenna put together. And this index were very important, as I told you on last day's class also, that H11 would indicate the receiver antenna 1 and transmitter antenna 1, like that, so on and so forth. So please make a note of it, or if you have already made a note of it, that this is an R cross T matrix and not T and R. So make sure that when you are representing this, or when you are writing it in your answers also, so the receiver comes first and then the transmitter comes in. So suppose it is a 2 cross 1 system, if I say in our case, sorry. So if it is a 2 cross 1 system we are talking about, then basically it is like, if it is H equals to 2 cross 1, it means 2 receiver and 1 transmitter antenna. Don't go the other way around. It's 2, 3 and R. That is not the case, because this is the common nomenclature. Okay, so please make a note of it. Now, keeping that in mind, we came across a very important objective, is that to find out that what will be the optimal optimal input, considering the fact that we have received some outcome, that is some noisy outcome. So that is where we found out another method, which is called as the zero forcing receiver. And the main objective over here was that for normally for R equals to T, or where we have a square matrix for that matter, we don't have, or even the smaller matrix, for example, the CISO condition, we don't have much problem in making the calculation with X, keeping in mind that we can take a conventional H inverse and we can multiply with the received outcomes, and we can find out what is X. But the problem comes in when R is greater than T, or we don't have a square matrix. That is where we come across a problem. And that is where, if you need to find out, one of the method that we come across is called as the zero forcing method or zero forcing receiver, where we are having a cost function which is given by the minimum of y minus hx, where we have to make sure that given an optimal value of x, this particular cost function should give you the least outcome. So that is basically what the objective is. Keeping that in mind, we also found out that this all comes down to only one segment, and that is the most important relationship, which is given by x equals to H transpose H inverse multiplied by H transpose into Y. Please make a note of this, very important in that way, because if you see over here, the question that we have come across, or the questions mostly we are looking at, due to the limitation of our calculation and to restrict our calculation for that matter, in most of the cases the H will be provided in your real values. It won't be a complex values. All right. So as they are real values, so we will consider this as the transpose. So this equation only is efficient, or it is necessary for solving the questions. But if suppose H is given in a complex term, then this transpose is replaced by the Hermitian operator. Now this Hermitian operator or the transpose operation, I think in your calculators you already have that option. If I'm correct, am I correct? In transpose is there. Hermitian is not there. And as far as the inverse is concerned, inverse is also there. So that's why if it is transpose and inverse, that's why most probably in most of our calculation also, whatever we are going to get, we will restrict ourselves to mostly transpose and inverse. But in general, if I say the general mode, and when we come across a research probe like on that, this is ideally the equation. All right. So basically, this is the equation that you should remember. H Hermitian, H inverse, H Hermitian. So this is basically the equation that we are going to refer to. And given the fact that we have a real value data, this Hermitian can be replaced just by the transpose of it. That's all. All right. So keeping that in mind, we found out that this is basically the equation, the final equation. So numericals might come in, which we are going to solve right now, that we need to find out what is my optimal value of this FZF. All right. So we found out that what is FZF. So FZF is nothing but the factor which is given over here. So you'll be provided with a H matrix. From there, you need to find out what is FZF. And from there, you actually can decode that what actually has come as outcome. So let's see with a question, then we'll move forward with the same. So let's see that with a one of its kind of a numerical. So suppose this is because this questions, no, these are very similar. We will change the data over here in the matrix, but the operations and everything will remain the same. As I said, these operations are matrix manipulations. So that remains the same, except the data will vary. So read the question once again. Given a channel matrix of 1, minus 0.8, 0.2 and 1. So it's a 2 cross 2 matrix. R and T is equal to here, and they are all real valued values. So we are considering the H transpose case here. And the transmitted power is minus 3 dB. And for each, on each of the transmitted antenna, which is given by a expression of this sort. We consider it to be minus 3 dB of power. Question is, let PPSK modulation is used for each antenna. That means plus 1 and minus 1 is allotted for bits 1 bit at a time. So if it is negative, if it is less than 1, or if it is negative value, then we will consider it to be minus 1. If it is more than a positive value, if the outcome is positive, then we will consider it plus 1. So that's how the modulation will work. The question is, the first question is, derive the ZF receiver decoding matrix for the same. Alright, so this is a very, very typical question, and it's very common to all this type of question. Just the matrix will change and the operations will remain almost the same. Okay, so as you can see, I have written down the basic equations once again. So this is basically what we already know. Alright, now what we have mentioned over here, that all the channel matrix are over here is real. So we can consider the H Hermitian to be H transpose in nature. So that's all the only changes that we have in the equation. So the question is to find out this H transpose, H inverse multiplied by H transpose. So H is already given to you, right? So you can just directly substitute in your calculators. Hopefully, I didn't do that. I did in the long process of manually doing it, so that we have the understanding of it. So accordingly, we can say H transpose is nothing but what is there in H. So we have just transpose it to 1, 0.2, 0.8. As you know, row and columns are getting shifted. So that's all we did. Now, as you can see, I have specifically mentioned one thing over here. While you are doing the same, because some of you might make this mistake, please don't do H multiplied by H transpose. Then don't do this, because as you can see over here, we could do this only when H is square matrix. In our case, it is a square matrix, so we can do this and we'll get the same result. But as in a general case, if suppose the matrix is not square, which is over here, if suppose this is a 3 cross 2 matrix, okay, so suppose in the question it comes in as a 3 cross 2 matrix, it is not a square matrix then. So what we are going to follow is, we are going to follow H transpose H. This is all we are going to follow. Please make a note of it. Always this, because this H transpose for non-square matrix, it is not same. H equals to H transpose, H transpose is only equal to H transpose H, given that H is a square matrix. Alright, but if suppose in general case, R and T might not be equal. So if you are doing that over here, this is wrong. This is not equal. So that's why, to keep it in a general mode, to keep it in a general calculation, H transpose H only you are supposed to find out. Don't do the other way around. It's not a good practice actually. Okay, only because if you are doing H transpose, it's a square matrix specification. But given in a question, if it is non-square, you might find that the answer is itself wrong. So don't do that. As per the property of the matrix, you cannot do that. Okay. So H transpose H, so we are just multiplying the same, just substituting it over here. I've given the individual steps also for anyone to just have a doubt or anything for that matter. But anyway, I think in your calculator, if you can substitute the data, it will give you the final answers. So that will be the H transpose H. Now the only portion that comes in is, in the formula, if you go back, we have to take the inverse of it. Alright, so we take the inverse of it. So we have to take HCH inverse. So this inverse you have to take. Now matrix inverse, this also, I guess many of you already know it. But just to recap, because it's just a matrix manipulation. So I've just given over here that how to find out the matrix inverse as well. So just for your convenience, you can do that. So matrix inverse is usually 1 by determinant of the matrix by adjoint of the cofactor matrix. So this is where I've given the separate calculation. So determinant I have found out. I guess already you know it, but still just a practice of it. So this is your value. Alright, similarly the cofactor matrix, I guess anyone have a doubt with the cofactor matrix? Cofactor usually is like, you take this column out, you take this column out, take this row out, whatever the element we are present with, this will be the first element in the next cofactor. That will be the cofactor. Alright, so that is how we usually do it, and we follow the sign. I think here I have mentioned find the minor of each element. That is basically how the minor is calculated. So second one would be like, if I take another color, maybe I'll take yellow. So suppose the second element, how will it be? It will be like this and this. So you are left with -1, but we have to follow the pattern like this. Plus, minus, minus, plus, like this. So minus of -1 is +1, so that's why it is 1. Alright, so this is like these are all practically from the matrix manipulation, nothing to do with the communication as such. So as I keep on telling you, please go back and refresh your ideas on covariance or cofactor matrix or adjoint of a matrix, transpose of a matrix. Please do that. Okay. So that is how we found out the cofactor matrix. Now we got the adjoint, which is nothing but this. All right. Okay. And then we substitute everything. So we substitute over everything and we get all the calculations done. So we get a matrix of that nature. So this is your inverse calculation part of everything. This mostly will be done. Just confirm me, is it all done, can be done through calculators? Because I'm not very sure about it. I mean, I did it on the basic way of doing it. I haven't used the calculator as such. I've done the hard way around just to make myself available. But is it available in calculator? Can we do that? Okay, fine. So there will not much be a problem. Now we come back to multiplying that last portion. This is all we have got multiplied by the H transpose of it. So this is again the steps to do it. And finally we get an FZF, which is the question to ask that what will be the optimal array or optimal vector for the zero forcing receiver. So this is my element. So this was a question that find out the zero forcing receiver for the same given that H is given. So if you are changed with the H, the same procedure needs to be followed. Provided that you have calculated it correctly, you should be getting a unique answer for this FZF. But if you are doing any problem, any mistake in the associated calculation, you will have problems. Alright. Now the question is, that is where it is very interesting. You can observe that what is the impact of this ZF receiver. Now the second question is, let the receiver or the receive vector that we are receiving is y equals to -1.5 and 0.27. This you understand very clearly and quickly, because this is the main reason why we are doing this process. So we have found out a ZF or a optimal zero forcing receiver. Now the question is that we have received some y, we have received some outcome. We have to find out, decode the transmitted symbol. What is the transmitted symbol? You get it back. Now, provided that we are using BPSK modulation at each of the transmitted antenna. Okay. So the basic formula, if I go back to where we actually had ended our discussion last day. So X is nothing but the FZF multiplied by Y. Right? So we go back to this question once again. So the same thing we have done here. So FZF multiplied by Y. FZF we have just now found out. Y is already provided to us. We just do the normal multiplication and we get a answer of this nature. Okay? So for the given Y, we have got some values of X, which is given, this may be given by X1 and this may be given by X2. Okay? Now the question you can see that but this is not the decode, because remember the transmitted data is nothing but some kind of a BPSK modulated symbols, right? So ideally we are looking at a scenario where ones and zeros have been sent, because it's a digital data for that matter. So the question here is that what will be the outcome after this? So you can see what I have written here, that as it is a BPSK modulation, we have the negative estimate will be always -1 as per the principle, and positive estimates will always be +1. Or we can say this -1 corresponds to 0 and +1 is corresponding to 1. That is how BPSK works. Ones and zeros will only be taken care of. Zeros will be -1, ones will be +1. So you have got this value. So -1 and +1 are the two extreme ends. If you remember the spectrum of BPSK, usually it is something like this. So this is your -1, this is your +1. That's how usually the spreading is. Constellation, what we call it. So this is how it is. So now given the value of X1 and X2, what we can say that it is relating to -1 only. You can see both of them are negative. Both of them are negative value. So negative mean, as per our logic, as we have discussed, or normally what we consider, negative estimate means it's a -1. Hence X1, this X1 is nothing but a -1. Whereas this one also is a negative, so it is -1. And again, this -1 relates to something like a 0 and 0. So basically what I mean is that the transmitted data most probably at the transmitter would be a 0-0 factor. So this was the data which was transmitted over the air interface, which we have received, and the receiver is now showing the outcome after the channel and everything modification has happened. So ideally the decoded transmitted symbol is -1, -1, but as -1, -1 is again indicating to 0, so we can say the transmitted data which was there is ideally 0. So you can understand the loop that we are looking at. So we are trying to find out FZF, keeping in mind that FZF is derived on the basis of minimizing the error between Y minus HX. So we found out a matrix or an optimal zero forcing receiver. We have found out with respect to that particular channel. Based on that zero forcing receiver and given the received signal, we can come back and we can reciprocate and we can find out what are my optimal input which was sent on the transmitter. So this is a very, very typical question from zero forcing receiver, which you might expect even in your exams as well, where you have to just get on calculating it. Now remember, this is we have done for 2 cross 2. If it is 3 cross 2, process will be the same, except that the dimension and the calculation will be done in your own way. But the process will be the same. That's all. Okay? Even in your example, again, I guess last day when we were talking about, I think in here, if you observe that when we were doing last day's class, I had given you one example like this. So in this case, R and 2E was different, but the process involved was same. We have done the same thing. Okay, so HC we have calculated because of the real value, and the same calculation yielded us some results like this. Same thing we have done. But in this case, the difference was that we didn't knew about Y. So the final expression that we had was a function, a linear function. This is why it is called as linear receiver. There are some non-linear receivers as well, which we are not going to discuss much right now, or even I don't think after CAT as well. But there are some non-linear receiver as well. This is a linear receiver. Alright, so you know the values of Y1, Y2, Y3, you can find the value of X1. So the same question, suppose I add up, the same question I add up by giving a Y matrix, why there are some values given. 2, 3, 2, suppose. So you substitute the values over here, estimate everything, you will get some value of plus or minus. Now suppose you are sending the data by BPSK, then basically it is a plus 1 or -1. Accordingly, you can choose whether 0 was sent or 1 was sent. Am I clear with this? Am I clear with the process? Alright. So this is about the zero forcing receiver. That is very common and you can expect a question out of it. The other part of it, can I move on? This is fine, everyone, with the numerical? Alright. The other part that we come across, which I'll just touch upon because this is not I would say we don't need that much of interest as it stands right now, because we already have a lot of things done already. But this is for your information actually. This is the other one which is more advantageous, I would say, compared to zero forcing receiver. There is a specific reason for it actually. That is what I wanted to tell you, and only that portion only is relevant for us. We don't have any numericals or as such, but we just need to understand that this is also the practical implementation of such receiver, and that is called as the MIMO minimum mean squared error receiver. Okay, this is something which is a little advancement to what the zero forcing does. Now, one of the biggest drawback with zero forcing receiver is, that is given over here, is that if suppose R and T is equal to 1, alright, that means there are only one single link between the transmitter and receiver, and you have the equation which is just now we have done FZF is equal to H transpose, H inverse and H. So all this comes down to something like 1 by H. So you can see over here, it's only that this value is coming in. Because of the same case, because it's a one constant dimension, so altogether the Hermitian or the transpose will give you 1. So that is how it is. So you get a 1 by H. Now the problem here is that if you substitute over here in this equation, XZF equals to FZF into Y. Just now we did that, right? So in there, FZF you substitute 1 by H. Alright, and you have Hx plus N coming in from the portion of Y. So what we are getting is that you can say over here that this N by H is a factor which is appearing over here. Okay, this one, the last right hand side. Now you can see when H is very close to 0. Okay, if the channel somehow is very close to 0, then this is becoming a very problematic scenario. Because if this denominator is the denominator is 0, then basically that N is a noise factor, right? So it increases the noise. So when H is relatively equal to 0, because H is nothing but the matrix which you are getting outcome of the multipath scenario. So supposing in a given scenario where H is almost equal to 0, then this portion or zero forcing receiver is giving us a noise amplification. That is called as noise amplification. So unnecessarily the noise will increase in the circuit, which you are supposed to reduce, but it increases. Alright, so that is the major drawback with this particular case, and that comes in inherently from the equations point of view. Nothing to do with the design of it or the principle of it. It's just that from the equation inherently it comes in. Alright, so this noise amplification is significantly reduced when we go for the second one or the more used one, which is called as the MMSE receiver. Minimum mean square error, I think almost all of you have we have talked about this in long back. If you remember in case of our first module, where we were talking about the practical link budget calculation, there also I told you the XMMSE, how the MMSE is calculated. Received data minus the estimated data. So theoretical minus estimated, like that. So that difference is basically the mean square error. Okay, square root of xi minus xi estimated. So that same thing is happening over here. Just like in zero forcing, we have a cost function. Here also the cost function is something like this. Minimize the error. So you can see XMMSE is the estimated symbol error minus that of the transmit vector, which is x. Same as that last time. Last time it was, for zero forcing, it was y minus h of x. Okay, here it is x of both are x. So one is what we have received at the outcome minus what it was transmitted at the transmitter. So that difference, that should be minimized. That is basically your cost function. This is your cost function. Just like in case of zero forcing, it was a cost function. Here also there is a cost function. Now, based on this, the calculations are there, which again I would try to not to do right now because it will take a lot of time to go through. But I'll just give you a one small information which I think you should keep a note of it. That is the final expression that we come across. This one you please make note of it if at all it is important to you. That is over here when you remember the formula that we got for XZF. So it was XZF equals to FZF multiplied by Y. This was for zero forcing. Alright, this was for zero forcing. So same way we are trying to find out something as X in terms of some kind of a matrix which is coming from MMSE multiplied by that of Y. So it's like related to that. That's why I've given you. So please make a note of this last expression which is present over here. Alright, so PD is happens to be the power that is coming in from the transmitted symbols. Alright, so PD, you can see over here, PD into H inverse, Hermitian H plus sigma n square plus I. So you can see here itself, there is a portion of noise included. But there is a approximately that will be removed as well. But this is how the expression would look like. So you can say this whole thing that you are looking at, this is maybe I can say f of MMSE. This is a function, the overall function. Alright. So this x again, x equal to f MMSE multiplied by y. Now interestingly what happens is this is the final outcome. Okay, this is the final outcome. Now, in terms of noise, if you say, so you can see here, if I go on just substituting that equation once again, okay, inverse and everything, and in the same manner when h is tending to 0, alright, what will happen is that you can see that if I recalibrate the equation a little bit, we don't have any such denominator term in the final expression. Interesting is this one. When it is a high SNR value, that is when the H is equal to 0, like we are comparing the noisy environment, you can see the XMMSC is given by this part. Alright, so the factor that we are looking about. So PDH by PDH inverse, everything is same. Okay. Now if I do H equal to 0 over here, we are only left with something that sigma and H inverse does not have H as the denominator of ZF. H on numerator is not a problem. That is fine. We will have a 0 anyway. But denominator, if it is, that is the problem. So we have eliminated the denominator H. So that is why what happens is that for MMSC, it gives you a better result compared to zero forcing in terms of the noise amplification is concerned. So it doesn't necessarily will increase the noise. And also it will provide a better resolution as well. Alright, so that is the only thing you should know about it. That MMS is better than it is. The other part that you should take a note of is that given that is what an interesting result, that is given that we have this equation. Please focus on this carefully. Given this as an equation, when we have a high SNR, when this P by sigma n square is tending towards infinity, very high SNR, you should recollect that in many of the cases we have taken some approximation when the SNR is high. Even in BR we have taken that approximation. For high SNR, some approximate PR expressions we have derived. Alright. So same way, if a high SNR is there and PD by sigma n square is almost equal to infinity, then we are looking at a scenario that this PD H inverse H plus sigma n square I, this will be almost equivalent to PD H inverse or PG H Hermitian H. Which in fact says that if you substitute over here, you are getting an expression which looks very similar, and this is nothing but the zero forcing equation you are getting. You can see here, it is absolutely similar, although you are calculating X MMSC, but the equation when you are deriving it, it approximately comes back to almost like a zero forcing receiver. So all the advantage of zero forcing receiver, if any, that is again already there for MMSC at high SNR, including the noise amplification, which is significantly lower. So that is why one of the biggest advantage of MMSC to be used. Alright. So at high SNR, just remember this last line exactly, that at high SNR, X MMSC can be approximated to X ZF receiver, which is a significant finding. That is one thing. And if at low SNR also, it also works as a mass filter proportional to H inverse. That is not entirely needed, just an information of it. So at low SNR or at high SNR, this MMSC is a generic case, you can say. So high SNR, it will almost behave like a zero forcing receiver. So we have discussed about the two receivers for that matter. Both of them are linear in fact, and both of them indicate one of the factors that there is a cost function based on which one wants to optimize the input data, and based on the matrix, final matrix, you can say in this question also, suppose you are given a question like this, only the thing that you only have to have is to solve this. Alright, but naturally you can say the complexity is little bit more because this calculation at normal general equation, you need the value of PD, the power, you have to multiply that. You have to have a finding of sigma n square, which is basically a noise factor. That also you need to have a data. You can substitute and you can like get that answer also. You will get a matrix of some sort. Because in between you only have H Hermitian H, which is again you are doing as for ZF. So it's very similar. Okay, but the equation is a little difficult, I feel, especially when you are doing it without looking at the equations or while in the term and when you are not having the resources with you. For CAT2, it is still okay, you have the formula, but the calculation will be a little rigorous. That's what I feel. So, but for the timing, you should know that how they are compared. That's all. All right. Anyone? Any doubt? Okay. So this is about the receivers that we have for us for understanding. The last portion that we have for us, and that is very important tool. We discuss about a very important tool, and most probably we'll solve some question today and maybe a little bit question on Wednesday's class as well. And that question is not, and that portion that we're looking at is something called as signal can be defined by something called as singular value decomposition for the MIMO channel. Alright, we call it the SVD. SVD is already there. We usually do it for the matrix calculation also we do it. But the significance of it in terms of our wireless system is what we are looking at. Because you can see that all these operations that we have come across, these are generic matrix operations. These are there. Alright, but how that can be related to our work with respect to our study is what is important. So as of now, what we have observed in MIMO, that everything is a little bit complex compared to what it was for CISO. Be it the BER calculation, be it the system model, be it the receiver, or the conceptually also, it is a little bit tedious to do at times. Alright. And similarly, if you consider that there are multiple antennas and multiple receivers, and you have that H matrix or the transposition matrix, okay, transition matrix, which looks a bit complex when you have complex data in it, it is very difficult at times to figure out that what exactly needs to be done or what needs to be processed. So for that you can see there is this tool SVD is used to characterize the MIMO channel. It's a very, very important tool that is used for specifically for MIMO scenario. It is not that much effective without when there is no MIMO or CISO system, or even for SIMO also it is not that effective. For MIMO it is absolutely essential. So decomposition of channel matrix into simpler components. That's what the main objective is. Alright. So we try to decompose the complex channel into comparatively simpler components, and from each component we extract out some information. And those extra information will indirectly give us some information. That's all. Okay. So let's see. So you can see here another statement here. The decomposition transforms the MIMO channel into parallel independent subchannels. Now, why it is important? Because you are when you are analyzing, you are considering all the channels merged up together. But this process will try to segregate them out, and they will assume that all the channels are not dependent on each other. So they are like independent identities. So that's why parallel independent subchannel. Now, if they are parallel independent subchannel, ideally we have easier analysis. No dependency. One channel doesn't depend on the other. So that dependency is completely erased if you are going forward with this SVD process. That is very, very important. When you have a very complex channel, it will be a problem. And last but not the least, it is also acting for the non-square matrix as well. So when R and T are different of different size, we don't have any problem. If it is of square matrix, so it is not a problem. But if it is, even if it is not in size, we can go ahead with the SVD as well. So that is why it is a general rule or general tool, I would say, in order to use it for the MIMO channel. Now the main combination of it, please make a note of this only equation. I'll tell you exactly what we need to do. It is a general notation. This is a general notation for an SVD. So the H channel matrix that you have can be constituted or decomposed. That's a correct word. It can be decomposed into 3 specific arrays. Alright, or 3 specific matrix. If I happens to just show you that. So these are the 3 matrix. Okay? So first matrix is called as U. It doesn't have any name as such. It's all are you can see unitary matrix which is mentioned over there. So this is one matrix U. The other matrix of the sigma over here is nothing but the capital sigma is given by some delta values, which are nothing but a noise factor, you can say in that way. Or we will see that what is the significance of it. It's a diagonal matrix that you are looking at. And last but not the least, there is a V Hermitian matrix. Okay, on the right hand side. So these three are the basic constitute. It means whenever you are given an array of age, you are supposed to break them out or break them or decompose them into three specific matrices. That's all. U, sigma and V Hermitian. And as this matrix will have certain properties, you need to figure out whether those matrices are following the properties or not. If they are following it, we can say that that is a proper decomposed outcome. Now, what is the outcome? What is the reason for doing it? We have established that basically we are trying to analyze a complex channel. But what about the significance outcome of U and V, or for that matter sigma or the capital sigma? We'll see that in next time. All right. So let's see the properties. Please make a note of these properties, because this is very, very important from leading from this point, because all the questions related to this sums up to come somewhere down these properties, whether pure decomposition follows these properties or not. All right. So in this case, you can see over here, as their unitary matrix, some of the cases are coming in directly from the matrix point of view. For example, the fourth one, U Hermitian U is equal to always an identity matrix of T cross T. Okay, so please make a note of this these properties, and even if you are in your question it comes in, I'll show you some of the type of questions also. You need to find out a way to prove all this one by one, so that your decomposition is actually following the rules or not. That's all. So first thing is the norm of it. So you can see U square is equal to Vi square equals to 1. And the second one is very important, which is the U of U Hermitian multiplied by J, because these are commonly coming in from the matrix point of view. And this also sums up that the columns are orthonormal. How do you get the orthonormal columns? Can anyone tell me? For matrix, how do you get the orthonormal column? Norm of the vectors is equal to 1. Alright, so that is usually orthonormal. So when you are decomposing it, the U's, that is, you should have a scenario where this is happening. Okay, so we have to test that accordingly. We'll see that with an example. Next is, you can see over here, V also has a property. V Hermitian V, it should always be V Hermitian, VA Hermitian and I. So both of them are identity matrix with T cross T. Okay, so you are supposed to get that. So if it is R cross T and R and T are equals to 2 cross 2, that means you are supposed to get the identity matrix of 2 cross 2. That is what the objective is. Okay. So with the calculation, we will get that. The numericals will understand this. Now comes the sigma effect. Okay. So the capital sigma is given by a factor as this is the last part of it. Please make a note. I'll tell you what to know. That equation that you write, sigma equal to sigma 1, diagonally all are sigma t. So in that, the property is that sigma 1 should always be greater than sigma 2. Okay, please make a note of this. sigma 1 is greater than sigma 2. That is one important segment. Okay, so this is one very important segment. Sigma 1 should always be greater than sigma 2. This will be very important later on. Singular values are the non-negative and the arranged in the decreasing order of magnitude. Please make a note of this. This is very important. The reason is, so these are the properties, right? So let us end on that note itself. So one of the important information that is why we are dealing with U and V. U and V are these matrices which gives us the information about beamforming as the transmitter and the receiver. Beamforming as a technique we might not be discussing in this class as such, but beamforming in general is a process in which we are trying to estimate the density of user and accordingly we are redirecting the power towards that particular set of users for better coverage. That is how the beamforming works. So you can see the alignment of transmitted signal will be based on the strongest singular values and that will direct the direction. Okay, it's a direction. So the beamforming, for that, you need the values that you are getting out of that U and V matrix. So you have a channel matrix, you know for a multipath scenario, oh, this is my channel matrix. You are decomposing it into U, V and the sigma part. And if you get that values, the higher the values, the alignment that you are looking at, that will give you the direction. So that's an information that you are extracting out of it. That's what I told you. And similarly, improve signal quality as it is improving signal quality, reducing the interference. So that's one of the information. Secondly, please make a note of this, the rank of the channel matrix, which is nothing but the non-zero singular values. Here, in this case, these values, how many non-zero values that you are getting, all right? That is basically giving you the rank of the matrix. This tells you how many independent data stream can be transmitted over the channel transmitted simultaneously. So if suppose the singular value are getting 3, suppose the non-singular values are 3, then it means 3 such independent channel exists through which the transmitted signal might happen. So these are some of the information. You can see the larger the singular value, the strongest is the independent part, which means result into higher capacity. So basically the logic is that from the complex channel, we are not able to process that. So we are figuring out a process in which we make it decompose into simpler ones. And those simpler ones will give us some information. We are assuming extracting some information from those matrices. So that is being done over here. For example, this is a very simple one. We'll take a little bit more next day. Suppose this is a CMO system. All right. Now, given the H is a very simple matrix, H 1 cross 1. All right, like 1 and 1. So in column it is given R is equal to 2, T equals to 1. Now we have to prove all the properties and we have to divide that U, sigma and V Hermitian. So usually this can be done in a process of this nature, keeping in mind that all the properties needs to be maintained. Now, if you ask me, sir, how do I know that this segregation will take place in this order? For that, you need something called as eigenvalue calculations, which we are not doing right now. All right, with respect to eigenvalue calculation, we actually can get it. When we are doing it, the question that we are going to solve, you will find that will be more intuitive in how you can segregate it. I'll tell you that process also. Now, in this, you can observe that we have segregated that matrix into 3 halves. Okay, and we are calling this as U, sigma and V Hermitian. And later, we are trying to prove all the properties one by one. And finally, we are getting, as you can see, property 5, property 6, everything is maintained. And finally, we are saying that all the properties are maintained of the matrix. So we can say that this U, V and sigma is a proper SVD of the channel matrix 1, 1. Alright, so that is how it is. Usually the process is, so we can look into such questions and we can find out whether the properties are maintained or not. So next day when we come back, we are going to take some examples of SVD, which are little bit simpler in a way, but we have to understand that how the properties needs to be framed. Alright, so that is all we'll do on Wednesday's class and the final suggestions for what you need to focus on more, and maybe we can talk about few more numericals along. Okay, take it.